Hi, my name is Sue and it's my pleasure today to introduce Neural Semantic Fields, or NeSF, a new method for full 3D scene segmentation. We begin by describing the problem we aim to solve, the semantic segmentation of a 3D scene. While segmentation of images is a well-studied task in computer vision, what does it really mean to segment a scene in 3D? Consider the scene pictured here. We might place a camera in the world, take a photo, and apply a conventional 2D segmentation method. This will produce a 2D semantic map, which we then might use to answer downstream questions. But what happens if we move the camera over here? We can again apply our 2D segmentation method, but we can't guarantee that the new predictions will be consistent with the previous semantic map. Moreover, how can we back-project our 2D predictions into 3D space and assign labels to query points like these? What we really want is something more, a full, dense 3D reconstruction and semantic segmentation of the entire scene. In other words, a method for assigning every point in 3D space a semantic category while simultaneously reasoning about object occlusions. Even more, we desire a method that can be trained and applied using nothing more than 2D inputs such as RGB photos and semantic maps. Such a method could then be used in any setting where monocular videos and labeled semantic maps are available. We now introduce neural semantic fields, our method for 3D scene segmentation. Our pipeline begins with a set of 2D RGB images describing a 3D scene. The first stage is the recovery of intrinsic and extrinsic camera parameters for each RGB image. These parameters allow us to place these images in a 3D scene and give us a direct connection between individual pixels and 3D camera rays. Camera parameters can be easily recovered using off-the-shelf tools such as Colmap. For this work, we assume camera parameters are readily provided. Next, we apply neural radiance fields to obtain an implicit volumetric representation of the scene's geometry. In particular, we obtain a density field, a function mapping 3D points to density. This function describes the 3D geometry of the objects in the scene. We then apply a semantic reasoning module to obtain a semantic field. A semantic field is a function mapping 3D points to probability distributions over semantic categories. Crucially, the semantic field is defined everywhere in space. That means that we can query NeSF at any 3D point and obtain a semantic categorization. In addition, we can combine NeSF's semantic field with the NeRF's density field to render semantic maps from any camera pose. This means that NeSF can generate semantic maps even when RGB information isn't available. As in NeRF, the semantic map rendering process is fully differentiable, meaning that NeSF's parameters can be optimized via 2D semantic supervision alone. As far as we're aware, NeSF is the first method to learn semantics from the geometry stored within 3D neural field representations. In order to evaluate NeSF, we require a dataset with a few distinct characteristics. In particular, consider a set of cameras describing a single scene. Each camera is defined by its intrinsic and extrinsic parameters. In order to train NeRF, we require 2D RGB images. And in order to train NeSF's semantic segmentation module, we also require ground truth 2D segmentation maps. And to evaluate NeSF in 3D, we further require semantically labeled point clouds. Such point clouds are readily constructed from camera parameters, semantic maps, and depth maps. Note that depth maps are only used for evaluation and are not needed for NeSF's training or inference pipelines. We describe a scene by aggregating information from multiple cameras, each corresponding to a triplet of images. A dataset is then built by aggregating information from multiple scenes. To this end, we introduce 3 datasets to be released upon publication: Clever, Toybox 5, and Toybox 13. Please see the paper for further details. Let's now dive into the experimental results. As not many comparable methods exist for NeSF, we first compare against competitive baselines in 2D image and 3D point cloud segmentation. While these methods do not offer all the capabilities of NeSF, we believe they are representative of existing work. Let's begin by comparing NeSF to DeepLab, a method for 2D image segmentation. On this dataset, we find that NeSF and DeepLab perform comparably according to mean intersection over union. We omit results for sparse confident as the method is not designed to produce 2D semantic maps. In this illustration, we see an example of a typical error made by these methods. We now compare NeSF to sparse confident, a method for 3D point cloud segmentation. In spite of being trained solely with 2D supervision, we find that NeSF's 3D accuracy is generally higher than its 2D accuracy. In this experiment, NeSF slightly underperforms sparse confident, but we emphasize that the latter is trained with labeled 3D point clouds. Unlike NeSF, sparse confident does not need to reason about occlusion and has access to flawless 3D geometry. When visualizing results, we find that NeSF's most common errors are between ambiguous semantic categories and geometries too small to be captured by its semantic reasoning module. To emphasize NeSF's 3D nature, we further evaluate 2D MIOU on cameras where RGB information is not available. In this setting, NeSF achieves identical accuracy as before, but DeepLab is no longer applicable. On Toybox 13, the baseline methods achieve significantly higher MIU than NeSF. We see this as an opportunity for future work and describe NeSF's limitations in the following. Let's now examine a few interesting properties of NeSF. By design, NeSF is 3D consistent. That means that no matter how we move the camera around the scene, NeSF respects the 3D geometry of the objects therein. Here we compare NeSF to DeepLab on two views of the same scene. Notice the orange sofa? In the top view, NeSF and DeepLab agree with the ground truth. On the bottom view, we see that DeepLab changes its classification from sofa to chair, while NeSF's remains the same. DeepLab's classification also changes for the partially obscured display. NeSF leverages NeRF's implicit representation of 3D geometry. When NeRF's reconstruction quality is poor, NeSF is expected to suffer as well. In this experiment, we evaluate NeSF using NeRF reconstructions of varying quality. In particular, we fit NeRF models with 5 to 100 RGB images per scene. As expected, NeRF reconstruction quality, as measured by PSNR and SSIM, increases as more images are provided. We further observe that NeSF's 2D and 3D MLU increase monotonically in the same way. Let's visually inspect semantic maps produced by NeSF. On the top, we present an RGB photo from 4 different scenes. On the bottom, we present the ground truth segmentation. As the number of RGB images presented to a NeRF increases, we observe NeSF producing segmentations of higher and higher quality. We now ask, how does NeSF's accuracy vary as a function of the number of semantic maps provided at training time? We start by training NeSF on 10 to 100 scenes with 25 segmentation maps per scene for supervision. As expected, 2D MIU increases as the number of training scenes increases. If we decrease the number of segmentation maps per scene to 10 or even 5, MIU remains unchanged. It's only when the number decreases to 2 or 1 we see that the accuracy decreases. This means that NeSF can generalize from as few as 1 labeled image per scene. In 3D, we see a similar trend. Finally, we present qualitative results unique to NeSF. We begin with a clever dataset. We render RGB, depth, and semantic animations from novel camera paths for a variety of train and novel scenes. We emphasize that these camera paths have no relation to the cameras used at train time. The RGB and depth map reconstructions are provided by NeRF, while the semantic segmentations are produced by NeSF's semantic reasoning module. On the left-hand side, we see animations derived from scenes observed at train time. On the right, we observe NeSF's predictions for novel scenes. Notice how NeSF seamlessly integrates object occlusion, multi-view consistency, and shape understanding. We now present animations derived from Toybox 5. Unlike with Clever, we find NeRF's density field to produce clouds. These are often interpreted by NeSF as the background class and may partially occlude the scene. Now, we compare NeSF to Semantic NeRF, an alternative method for generating 3D semantic fields. Unlike NeSF, Semantic NeRF models are optimized per scene and are supervised by DeepLab-generated pseudolabels. On the Toybox datasets, we find that NeSF outperforms Semantic NeRF. Comparatively, we observe NeSF produces fewer mislabeling errors in 2D views and overall fewer clouds as seen in 3D renders. Additionally, when simple image perturbations like novel textures are introduced, Semantic NeRF's accuracy drops dramatically while NeSF's remains the same. This is a direct consequence of the approaches taken by Semantic NeRF and NeSF towards semantic reasoning. While Semantic NeRF leverages DeepLab, which reasons about semantics in pixel space, NeSF infers semantics directly from 3D geometry. As a result, NeSF's performance is robust to variations in appearance, texture, and lighting by design. In summary, we present neural semantic fields, a method for full 3D scene segmentation. Our method takes a set of posed RGB images and produces a 3D semantic field, which can then be used to render novel segmentation maps or label 3D points. We note that NeSF is the first method to learn semantics from the geometry stored within 3D neural field representations. NeSF simultaneously provides 3 forms of generalization: to novel views within a scene, to novel objects within a category, and to novel scene layouts, all with posed 2D inputs alone. We note that NeSF is the first method to learn such semantics from the geometry stored within 3D neural field representations. Thank you for listening.